Okay, guys. Time to get started. We covered nomenclature of aldehydes and ketones. Yeah? Yeah? How we doing? Can we name this compound here?
Straight up, no.
Arachidone. Good effort, Mark.
I had to send it to myself.
Anybody got it?
Number that would appreciate it. Why?
Who has it? Who has it? Okay, we got a winner right here. Who? Name?
Would be 3, 4, 4, 5 tetramethyl cyclohexanone.
Yeah. 3, 4, 4, 5 tetramethyl cyclohexanone. Wow. It goes by a common name though.
Penguin. Penguin. Penguin.
Oh, it looks like a penguin, yeah. Let's do that.
He's like, penguin.
Anybody know that compound? Please do not try to name it by IUPAC. Sea lion.
I know this.
It is a ketone.
Testosterone, right, yeah. That's what it was.
We have a handout. It may be our last one. Oh, God. It is a doozy. It is a nice one. No, I'm just ACS study guide. Oh
I think, yeah.
We have a yellow handout, and we have one that you can print on your own. Any questions about lab? Lab report due in 1 week. When you come to lab. Questions about this? No questions? Everybody has the NMRs I sent by email about a month ago? Okay, we left off with imines. An imine is analogous to a carbonyl, except we replace the oxygen with a nitrogen. Imine. You can also have enamines. Imines and enamines. Okay, there's a couple of special types of imines. Hydrazomes and oximes. A hydrazone is where you make an imine using hydrazine. Hydrazine. Two nitrogens bonded together, hydrazine. When hydrogen reacts with an aldehyde ketone, only one amine reacts. Aldehyde ketone, primary amine, imine. Just ignore the other NH2. But it's there. So it's an imine that has a nitrogen bonded to the other nitrogen. That's called a hydrazone because it comes from reacting a hydrazine with a ketone or an aldehyde. It's a special type of imine. These are fairly easily made. You don't have to worry about the equilibrium because we have conjugation of this lone pair with the double bond, it's usually driven this way pretty well. Hydrazone, you do need to know these names. If you use hydroxylamine, this is hydroxylamine, it's a known compound, it's stable. Imine reacts with the aldehyde or ketone to give the imine, the OH there, that's called an oxime. It's just a special type of imine. We did the imine mechanism on previous page. Again, it's sort of driven by conjugation of this lone pair with the double bond plus water. Two special types of imines. Sometimes these are called derivatives. Sometimes you make a derivative of an aldehyde or ketone, maybe for melting point analysis. Okay, we will see imines in the next couple of reactions. We'll actually see hydrazones. One place here, we have a new chemical test. 2,4-DNP test. Stands for dinitrophenylhydrazone test. For an aldehyde or ketone. You react an aldehyde or ketone with this reagent here. This is 2,4-DNP. That's hydrazine. That's phenylhydrazine. This is 2,4-dinitrophenylhydrazine. The terminal amine reacts with the aldehyde or ketone to make the imine plus water. It's a hydrazone since you got the other nitrogen there. It's a 2,4-dinitrophenylhydrazone. Why is this a chemical test? Typically, these are very crystalline. They'll give a precipitate. It's usually yellow or orange. The chemical test works by, usually these are liquids or not as crystalline. You treat it with your reagent and you instantly get a precipitate because the reaction is pretty instantaneous. And when you see the precipitate, it's a positive test. Only aldehydes or ketones do this reaction, and thus only aldehydes or ketones give the precipitate, give the positive test. What would give a negative? Well, acid derivatives give a negative. For example, what if you maybe had this compound, which is an ester? Both of these are colorless liquids, right here in the vial. Is it an aldehyde or is it an ester? Well, treat it with 2,4-DNP and do the DNP test. Okay. Oh, I got a precipitate. This indicates it's which one? The aldehyde. Because esters don't do this chemistry. They don't give imines. If you attack carbonyl, you're not going to get an imine. The imine would look like, you know, you got your, all that here. You're not going to get that. You have a leaving group. You're not going to lose the oxygen as water. This amine will attack electrons up, back down, kick that off. Okay? Only aldehydes, ketones lose the oxygen as water. This has another leaving group. It's acid derivative chemistry. And this is going to be slower, where this is going to be pretty quick. In the end, acid derivatives don't do this chemistry. They don't give a precipitate. You only get a positive with aldehydes, ketones. So what if we get a positive DNP test, but then we get a negative Tollens? What kind of compound do you have if you have those two results? Positive DNP tells us it's aldehyde or ketone. Negative tolerance tells us it's
Not an alcohol.
not an aldehyde, so by default it is apparently a ketone. So we have a complementary chemical test. Questions about that? But the derivative you're making is a hydrazone. It's a 2,4-dinitrophenyl hydrazone. Again, it's for small molecular weight aldehydes, ketones, which tend to be liquids. If this is a solid, you're going to have difficulty doing the reaction and distinguishing between starting material and new product. Most of these low molecular weight aldehydes, ketones are liquids. Okay, next, Wolff-Kishner reduction. We saw this when we were doing aromatics, when we make arylation, Friedel-Crafts acylation. Such a product here, we can make this bond, then we can reduce off the oxygen and get a CH2, like this. Wolff-Kishner, what were the other two ways we did this? Clemenson reduction with the zinc, mercury, HCl, and the third was
PD catalytes.
you can just do it with hydrogen and like palladium or platinum or something. Clemenson reduction is very traditionally used. Wolff-Kishner is also traditional. The H2 is not as traditionally used, although it works. So we said we'd look at the mechanism later. Well, now is later. Wolff-Kishner. That's right, Mr. Wolff. Anybody know where that came from? Okay, we can do this reaction here. The first thing we form is the what? The hydrazone. The hydrazone is what's formed first. Plus water, right? That's just a special type of imine. The mechanism was done on previous page. Typically only one end of the hydrazine reacts. Once you get here, this lone pair is conjugated, so it's less reactive, less prone to doing another one. Okay, so how do we get from there to the end?
Base takes H.
It's actually pretty straightforward. For a long time, the mechanism wasn't known. One of the first things that was discovered about this, other than this, the reaction, can you imagine the first person to do this? Like, I'm going to try to make hydrazone. I don't know what they're trying to make, and I got this. What happened here? Where'd my carbonyl go? Well, one thing they've realized is you also form nitrogen gas in this reaction, N2, which is, of course, you learn in third grade, Lewis structure like that. So, how do we get there? Well, we include a base here. What does a base do? You learned this in third grade too. Bases do what?
Take the H.
They remove protons?
Yes.
Yeah. What protons are we going to remove? Well, think about it. Why would you want to remove these? They're still there. Which ones have been removed then when we get over there? The ones from the nitrogen. Nitrogen no longer contains protons, so remove them. So we have a base. The first step here is the base. These electrons take the H, leave electrons behind. What do we get? We get this anion plus what? Plus water. Is that reasonable to make that anion, to do this acid-base reaction? Yes. What type of stability does our anion have? it's an electronegative nitrogen. It's not as good as oxygen. Or what other stability does it have? It's resonance stabilized. These electrons can move here, and these can move here. What does that give? That's a resonance structure, right? Single bond between nitrogen. Now we have a double bond. We're trying to get a triple bond, so we're halfway there. What are we trying to get on this carbon? H's. Well, at this point, how about if this takes the H back? What does that give? Now I have an H there. Gives that. Now this is all in equilibrium. Very often it is. That's not an equilibrium. Plus what? Plus hydroxide. What do you want to do next?
Take the H off the end.
Take the H, leave electrons behind. NiN plus water. What do you want to do now? Now this is not going to be resonance, but this is what we got to do. These electrons then come here, and we're going to kick these off. Now this is actually a plain carbon. You might say it's going to be resonance stabilized, but that phenyl does not have to be there. This is a little bit suspect. What does this give though? What's here now?
Lone pair.
Lone pair, that's a minus charge, plus what?
Into and H.
There's our nitrogen gas, triple bond.
Plus water.
This is a plain carbon. We usually said you're not going to kick off a plain carbon. Well, I think actually here we do. This is one reason it requires a lot of heat. This reaction traditionally requires pretty high heat, 200, 300 degrees. There are ways to get the heat lower, but this is a little suspect from what we've usually said. What do we need to do to get final product?
Take H back.
This takes the H, come here, final product, right? Plus what?
Base.
Question. Is that a catalyst or not?
Yes.
Or is it a stoichiometric reagent? Catalyst. It's actually catalyst. It's reformed. Make hydrazone, and then it's a series of acid-base. Take proton off, put it back on. Take proton off. Right here is kind of, this may be the rate determining step, expelling this carbanion. As soon as it comes, it's going to take a proton from water. This is probably the difficult step here. Questions about the Wolff-Kishner reduction? Apparently Wolff and Kishner were tag team. Kind of like Mr. Wrestler #1 and Ric Flair. Pretty good mechanism, yeah? Everybody agree? Yeah. Yeah? Ron, you like it? All right, that's right. That's CSI Miami. Horatio. He'd always say that Wolf was one of the guys who was in the lab. He's talking about that's right, Mr. Wolf. You ever watch CSI Miami?
Yes.
He says it every time. He's like, should we run a GC mass spec? And he said, that's right, Mr. Wolf. Strecker. Let's make some amino acids. Let's make some amino acids. Then we'll make some meth.
Okay, cool. Yeah. You should live
If you turn over one page, meth, here's methamphetamine. Please, for next time, please provide 2 different syntheses of meth. Both using a reductive amination approach.
Let's go. Where am I going to get like
You remember the show Breaking Bad? At one point they were breaking into a chemical warehouse and they were trying to steal a reagent. That reagent could be used in one of those syntheses. And they were using it. It was a big drug. It had the name written on the drug.
Yeah.
Okay, let's first make some amino acids using the Strecker amino acid synthesis. You may see this in biochemistry. Starting with an aldehyde or ketone, usually your amino acids only have one R group. One of my favorite groups, KCN. I remember KCN and the Sunshine Band back in the 1970s.
Yeah, totally.
Yeah, I remember that.
Those were the days.
Y'all too young. KCN and ammonium chloride. We can get this product here. From here, that's just a acid derivative reaction. Hydrolyze the nitrile to the carboxylic acid. So that's really nothing new. How do we get this? If that was an OH, what would that functional group be called then? Right, cyanohydrin. This is sort of like a cyanohydrin. How do we get to this part? This comes from cyanide adding to an imine. Now we need another H here. Like I said, the next few reactions, we're going to see imines and hybrizones as sort of intermediates. Imine here. First off, this is sort of, what do we have here? Well, we got cyanide, all right? You got a cyanide source. Ammonium chloride. You could just use ammonia. But ammonium chloride's a solid. It's easier to use. Ammonia is a gas. Of course, if you take cyanide and react it with ammonium, I won't do full Lewis structures, we can get HCN plus ammonia. So this is an equilibrium. Cyanide can take an H. Okay? So essentially we've got this once we get it dissolved and the equilibrium establishes. But these two are gases. Would you rather just start with two solids? Ammonium chloride and sodium or potassium cyanide? So that's what we got there. What we got, okay? What do we get when we react an aldehyde with ammonia? Aldehyde to ketone with ammonia. Well, that's that, right? You get imine plus water. Now this can come in here. Now I'm showing this like this. I mean, you've got that H plus here. The Cl minus. This is really ammonia with HCl. Or if we forget about that, we made ACN, we can say, well, ACN is, remember when we did this earlier, we were like, well, is it strong enough to protonate carbonyl, or are we going to protonate afterwards? Well, I'll do it afterwards here. Cyanide adds, that's going to give, I'll keep that H there. I'll keep that there. Electrons up, we get this. And then if you want to protonate, then you can protonate, and there you go. There's a few different ways you can do this, depending on how you handle the proton, etc. But you got a source of ammonia, you got cyanide, and then there's an H plus that can be picked up along the way. So hopefully you can see how we get to that product here. If you want to protonate this first, and then have cyanide add, that's fine too. These can be isolated, and then when you treat it with aqueous acid, you can hydrolyze the nitrile to the carboxylic acid, and that's three chemistry. But what do we have here? It's an amino acid. And this alpha is where you have your R group. Okay? Alpha amino acid. Well, the alpha actually refers to where the amine is. The nitrogen's on the alpha. But the variation here is the R group on the alpha carbon, that's what varies to give you various amino acids. And how do you vary what's in the circle? Well, you just vary what's in the circle there. So this ends up being your alpha carbon of your alpha amino acid. And anybody know the name of that amino acid we made there on the... Tyrosine? No, tyrosine has an OH group, I believe. That's just phenylalanine, right? Or does phenylalanine may have a CH2. Yeah. Phenylalanine has a CH2 between the alpha carbon. So to make phenylalanine, we would want to start with a CH2 between them. Yeah. I'm not sure that's one of the 20 amino acids. And then I think phenylalanine with an OH on the end, I think that's tyrosine, I think. But you can vary, you can get all types of aldehydes, and you can thus make all types of amino acids. And some person by the name of Strecker sort of standardized this method. The big thing here is, do you understand the sequence of chemistry, mechanistic steps in forming this? I'm not sure the name of this functional group. It's not significant enough to learn it here. It's analogous to the cyanohydrin. It's got a name, but I can't recall it right now. Not that common. Okay. For practice, you can give a synthesis of leucine. And we'll look at that a little bit later, using the Strecker amino acid synthesis. Next reaction, reductive amination, E. What are we under here? What's the heading under A through E? What are we under here? What was A under? Reaction of amines to give imines. Okay, all this is under imines. Each time we've seen an imine, like a hydrazone or the Wolff-Kishner, we saw an imine right there in the structured amino acid synthesis. Where are we going to see an imine here? Well, Reductive amination. This is one of the top 10 reactions in organic chemistry. There's about 20 or so of these. Reductive amination. I actually referred to this in Organic 1 when we first looked at direct alkylation of nitrogen, said there'd be better ways in Organic 2. This is one of the most common better ways. Aldehyde ketone and an amine. Imine. Nothing new there. What can you do with imines though? Well, we could add a cyano group and we can get this functional group above. Do other things. One thing you can do is you can reduce this double bond. Okay? Now the nitrogen's drawn up here and over here is drawn that way, but it's the same thing. We now have a CN single bond. One H on carbon, now two H's on carbon. No H's on nitrogen, one. So basically the double bond was there and we now have an H on each atom. You can do this with hydrogen, just like if that was an alkene. Hydrogen and palladium, platinum, nickel, etc. And if you do it with hydrogen, the mechanism is you roll two H's from the metal, boom, come in. If you had to consider stereochemistry, you would notice they came in from the same side. So it's not an ionic mechanism. But you can also do this with sodium borohydride, because this is a polarized pi bond, like an aldehyde or ketone, or carbonyl. Now, if it's polarized, we can use a hydride source, and these electrons come in here, electrons up. And that gives what? We now have two H's there. Electrons up to give anion, right? And then what do we need to do to get the final product? We need an H plus source. We need a proton here. Okay? This can come from H plus workup, including just aqueous workup, water supply. If you're using sodium borohydride, though, you can also use a protic solvent, such as ethanol. And if you use ethanol, it'll supply the proton. And you're just going to make the anion here, but it's favored that way because an O anion is more stable than a nitrogen anion. So this is an ionic reduction, where you have ions. And this is how you reduced your imine in the lab, right? You made an imine and then you reduced it, sodium borohydride. You used one propanol as solvent. The one propanol supplied the proton. Or ethanol, any protic solvent. What have we done here, though? Chemistry should hopefully be pretty straightforward. Make imine and then reduce double bond. What have we done? First off, the product is just a plain amine. Amine. Not imine, but amine. It's condensed here. That's a secondary amine. So it's a way to make amines. It's a great way to indirectly add alkyl groups to amines. Is that what we did? We start with this amine. What did we add to the amine? We started with an amine, we have an amine, but we added this alkyl group, CH2 phenyl. The alkyl group comes from your aldehyde ketone. It's called a reductive amination because you make an imine and then you reduce it to the amine. You may see this reaction with aldehyde ketone as the main reagent, amine on the line, or you may see amine here and aldehyde ketone on the line. It doesn't matter, right? They're both in the same class. So you'd be on the lookout for imines and then reducing them. Of course, you don't have to just pull the product out of the air. You use product that becomes single bond, right? NH. Okay. Let's see how we do with this. This is one of the few of the top 10 reactions that doesn't have a chemist's name associated with it. The majority of them have a chemist's name, like the what? The Williams ether synthesis, or the Diels-Alder reaction. What are some others? Wolf-Kishner, Strecker amino acids. There's got to be others. Tollens reaction, that's kind of a test, but it's also the oxidation. Any others? We will see one in the next, maybe not today, but definitely next time, called the Wittig reaction. Wittig. We had Hoffman elimination. I'm sure there was a few others. Had to be at least 10, not 20. Okay. So what do? We made imine and then we reduced it. Now you can do that stepwise. You can make your imine, isolate it. Hey, look at my imine. Then you can reduce it. That's what you did in lab. But a lot of times you do it all in one reaction sequence, all in one flask, all combined. Can you do that? Yes, this works. What's going on there? Barbara?
Since we're only going to use like one of the hydrogens, is it making a hydride? Like what's happening with those electrons?
No, hydride added to the imine.
We don't.
Before I erase?
No. I mean like right here. So I assume.
Well, we don't have hydride here. We have hydrogen.
Right, but what I'm saying is, in the way I did it, if I did it right, the last step will be the carbonation of the hydroxyl group so that it can go away.
No, hold on.
Maybe I did it wrong.
First thing is you make imine. That's not a benzene ring. Make imine. There's the imine that's going to be formed from reacting aldehyde ketone with methylamine. And this is back to Roman numeral 1, the very beginning of this section. We made imine, we did mechanism, and there you go. Plus water. But if we have hydrogen included in here, it won't do anything until right now. What will it do to this compound? This double bond will become saturated like an alkene. Get rid of the double bond. Let's make that clearly a single bond. That's a single bond with an H here and an H here. Now typically we draw in H's on nitrogen, but we don't here. But there's now a new H there, but I'm not showing a charge. And that's what you get when you reduce to double bond. But that and that over there is the same thing. I've just got the bond rotated. Right? Everybody see it? So that's what, there we go. We made imine and then we reduced it. You can do it all together there. That works. That's a reductive amination that's done all combined, one flask. Let's try it this way though. Methylamine sodium borohydride. Okay, we got a different starting material, but it's the same chemistry. Does this work?
let's see, we make imine, nitrogen with methyl. We can put this in brackets. That kind of means it's not isolated. What is this going to do to this? Hydride adds, this is a different mechanism. Hydride adds electrons up. And this picks up a proton from solvent. There's got to be some solvent here or something, or you work it up with proton. Does this look good?
It's just using a different reducing agent.
Problem is this does not work. The one above works, this one does not. Why does this combine not work? So borohydride is going to reduce your ketone. Up here, hydrogen does not react with aldehyde's ketones unless this was aromatic. If this was aromatic, it would reduce it. Sort of benzylic. Typically, hydrogen won't. So borohydride reduces aldehyde's ketones, right? You can't say, okay, we know you like aldehyde's ketones, but we want you to just sit there. Because, again, we're looking at combining it. If you did it stepwise, fine. You can't combine this. Above, you can combine. Everybody with me? No good. But, of course, chemists want to combine. We have a new reagent that was developed. If you use sodium cyanoborohydride, it will work. What is sodium cyanoborohydride? We got a boron with 3 H's and a cyano group. That's a negative charge, and we got a sodium. One of the H's has been replaced with a cyano group. It's called sodium cyanoborohydride. Is this more or less reactive than sodium borohydride as a hydride source? It is a hydride source. Is it more reactive or less reactive?
Less reactive.
Why less reactive?
If it was more reactive, it would solve our.
It's one
True.
way to think about it.
Based on structure, though.
You've got the resonance, yeah.
Well, it's withdrawing.
Yeah.
Withdrawing. What is the withdrawing going to do to this?
It's going to make that.
It's gonna make it less
less negative.
Hey, boron, I know you got too many electrons, but guess what? I know you got too many electrons, but I like them, and I'm going to pull them. And we know that these bonds are not just there. The electrons can be just perturbed. The electrons are pulled away from the boron some. So it's not as negative. Since it's not as negative, it's not like, hey, H, you got to go. It's a little bit less reactive. Because it's less reactive, it will not react with aldehyde ketone, but it will reduce the imine still. In the end, this is your traditional, very nice reductive amination all in one shot. Amine, sodium cyanoborohydride, it will work. This works too. The problem is hydrogen gas is not as convenient because you can't just weigh it out on the balance. Sodium cyanoborohydride is a nice solid. It is expensive a little bit. That's why we didn't use it in lab. You guys made your imine and then reduced it with this. 2 separate reactions. You can't combine with sodium borohydride, but you can with sodium cyanoborohydride. So, reductive amination, you make imine, then the hydride reduces it. Less reactive hydride source. Predict products down below. You guys on the right do the first one. You guys on my left do the second one.
Then we'll look at the white handout, the one you printed on your own. Oxidative dealkylation. Okay, here. Aldehyde ketone amine, what's that going to make? There's the imine that will be made. Replace the oxygen with nitrogen, right? Plus water. But the reducing agent is going to reduce the double bond, and we're going to get what? We'll get that right there. There are two H's here. There was only one. I drew it in there. I did not draw them in there. What we essentially did, we started with an amine. We ended up with an amine. What did we add to our amine? An alkyl group. On the previous page, it said this is a great way to add alkyl groups, right? We actually added an ethyl. The ethyl came from the 2-carbon aldehyde. Questions? How do we do? Down here, aldehyde ketone amine. Replace oxygen with, by the way, this could be E or Z. Doesn't matter. Either one's going to give the same entropy. We do not have E or Z here, if possible. Then when we reduce it, we get what? Is that right?
Yep.
How about the one below? The one below only has one starting material and sodium cyanoborohydride. Any reactivity here? Aldehyde ketone amine, can these react? 1, 2, 3, 4, 5, 6. Nice 6-membered ring reacting. Yeah. If this loses water, what are we going to get? Six-membered ring, end, double bond, and methyl, right? And then we're going to reduce the double bond. It's just going to be a 6-membered ring. Oh, we lost the methyl. Let's connect the bonds. You have methyl there. We have a chiral carbon here. Is that going to be RS? This would be an easy answer by now. Racemic. Racemic, right? Nothing over here is optically active. Nothing over there can be either. The hydride can come in from the front. When the hydride comes in, the new H is going to be either forward or back. The hydride comes in from the front.
the hydride doesn't come in like this because over here, the H is either forward or back. I mean, if the H is forward, then that's back. That's where the H come in forward, but it could also come in from the back. Okay, let's look at an application here as we end. Next time, please have 2 syntheses of meth. 2 syntheses of meth. We'll look at which one is best. Okay, reductive amination. In the body, this process is often reversed in metabolism of drugs. For example, if you take amphetamine, amphetamine is metabolized by the reverse process. Your body oxidizes this to the imine. That's an oxidation, a removing agent. Your body's a amine oxidizing machine. Then the imine can be hydrolyzed because everything we're making is reversible, right? Hydrolyzed back to what? Aldehyde, ketone, and ammonia. So, it's known that amphetamine, this is a metabolite. If this is in humans, this example may came from guinea pigs or something. This is one of the cases where different animals metabolize amphetamine differently. But this is one group. This is actually the reverse of a reductive amination. How you would get such a product as a metabolite. Please take a look at that. Okay, guys, see some of you in lab this afternoon. Have a good day.